Hello grade 12s and welcome to another video from the answer series. In this video we draw your attention to the differences between conservative and non-conservative forces. This allows us to demonstrate when you may use the law of conservation of mechanical energy. Consider when you have an object lifted at a constant velocity. The net force equals 0. So Fa is equal to Fg in magnitude. We use the work definition, with delta x being the change in the height. And we see that the work done by the applied force leads to an increase in the potential energy of the object. We calculate the work done by the gravitational force using cos 180 degrees, because the delta H and the gravitational force vectors are in opposite directions. So the gravitational force does negative work. If the mechanical energy of a body remains unchanged, the force acting on it is a conservative force. The empirical test for a conservative force is zero work over a closed path. For example, if you climb a flight of stairs to any height and then return to the starting point, then the work done by gravity is zero. This is what makes gravitational force a conservative force. A conservative force is defined as a force for which the work done in moving an object between any 2 points is independent of the path taken. In contrast, a non-conservative force adds or removes mechanical energy from an object. The path taken determines just how much energy is gained or lost. For an example, an applied force working along a short path will add less energy than if the path was longer. Friction removes more and more energy when working along a long path. So the work done by a non-conservative force depends on the path taken. The idea of a conservative force leads to the idea of conserving mechanical energy. Eliminate any external non-conservative forces and mechanical energy is unchanged. Then any change in potential and kinetic energies are equal in magnitude but opposite in sign. We say that a system without any external forces is isolated. The pair of forces between the Earth and a free-falling object is an example of an isolated system if there are no other forces at play. An object swinging as a pendulum is an isolated system. Each part of the system, the Earth, the swinging object, the string, even the pin where the string is tied, all exert equal and opposite forces on each other. So there are no external forces adding or removing energy from the system. The same applies to an object sliding down a frictionless slope. The slope itself, the Earth, and the object form a closed system with internal pairs of forces only. In all three of these cases, the total mechanical energy, that is, the sum of the potential and kinetic energies, is the same at any point and at any time during the motion. Here is an example of a pendulum, A. It is a closed system until the moment that it strikes B. Pause the video now, read the question carefully, and then continue to have a look at the solution. Let's have a look at the solution. Mechanical energy is conserved during the downward swing. Substitute all the different values into the expanded form of the equation and get a collision velocity of 7,67 meters per second. We now have a collision between A and B. In that instant, momentum is conserved. A slows down to 3,47 meters per second when B gains momentum. A continues to swing upwards as B moves rapidly out of the way. The remaining mechanical energy is also conserved, and A reaches a height of 0.61 meters. Is the collision elastic? Only A had kinetic energy before the collision, 147 joules to be exact. After the collision, A has a reduced kinetic energy of 30.10 joules, and B has gained 63 joules of energy. Together, however, their combined kinetic energy is less than the original amount, so the collision is inelastic. Now it is time for you to try. If you have access to the 3-in-1 study guide, try question 31 and 33 on page 175 and question 1 on page 158. The answers can be found on pages 169 and 184. Here is a question from the 2-in-1 study guide. The 500-gram package experiences vertical projectile motion. In other words, it is an isolated system, except when passing through the branches of the tree. For that time interval, the branches exert a non-conservative force on the package. Pause the video at this stage and try yourself to solve the problem. Then continue the video to see whether or not you can apply these ideas successfully. We can use an equation of motion to determine that the maximum height of the package will be 5.10 meters. We get the same answer if we use the law of conservation of mechanical energy. Whenever you use this law, start with this expression and then expand. Here is the statement of the law of conservation of mechanical energy. Key words to remember are total, isolated, and constant, as they are easily overlooked, and yet they are essential conditions for the truth of the law. In question 8.3, we are restricted to energy principles. So we use conservation of mechanical energy from the moment the package leaves Amar's hands until it touches the branches. Here the statement is expanded, the various substitutions are done, and it yields an answer of 7.80 meters per second. This is from rounding off 7.7974, so this 0 must be given in the answer. Fortunately, we are only asked for the net work at this stage, which we get from the work energy theorem. Overall, the work is negative, so the package slows down. Will the package reach Escher? You could again use conservation of mechanical energy to find the actual height above the ground, or you can use an equation of motion. This will give you the height above the branches, 1.28 meters. So add 3.6 meters to that to see how high it gets above the ground. Or you can find the potential energy of the package at its maximum height and compare it to the kinetic energy as it leaves the branches. Whichever method you use, the package falls just short of Escher's outstretched hand. Amar had better be ready to catch it again on the way down.
If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from The Answer Series, your key to exam success.